Hello, I'm Simon and I would like to teach you quantum chip design. Here you can see our fabricated quantum chip. It's 7-qubit system from IBM. It uses 6 normal transmons with 2 pin ports and one center flux tunable transmon. Let's take a look at the quantum chip design workflow. We start with concept where we define our topology, type of qubits, number of qubits, frequencies, and let's say type of fabrication process and materials. Then we move to lumped elements where we do equivalent of the quantum chip using lumped elements. From this step, we will move to circuit simulation. In this step, we simulate frequencies, S parameters, and additionally impedance profiles. Once we have our circuit simulation done, we are quite ready to move to layout since we know all the necessary parameters. Uh, So we do layout with our Qiskit model. Um, Once we have our layout done, we can move to FEM simulation, where we validate our frequencies as parameters. We can also simulate capacitances and parameters of resonators. We can also run electric field simulation and EPR. Once we are done with this step, we verified all the values. We can move to fabrication. In this step, we generate GDSI files and we need to check them if everything is correct. And if everything is truly correct, we can push our quantum chip to production. For this step, we can use probably almost every foundry you can think of. The only thing is they need to have capability to manufacture Josephson junction, which is thin aluminum rectangle. I can think of Skywater, Effabless, maybe some um, university fabs or institute fabricators. Let's take a look at the paper from IBM. We take inspiration from this paper. It's called Hardware Efficient Variational Quantum Eigensolver for Small Molecules and Quantum Magnets. Here you can see our layout of quantum chip. There is also some description about algorithm. We can scroll down there to see layout. There is layout with connections to the quantum computer. There is also some description about our hardware of quantum chip. It tells us more about nature of our quantum chip. As you can see, there is, for the experiments discussed in this paper, we use 6 of these qubits, including the central flux tunable qubit. There is also a little information about resonators and also about fabrication of quantum chips, type of process used to actually fabricate this quantum chip, and materials used for this process. it uses aluminum-based juice injection. Here you can see frequencies of our qubit. Here is frequency of a first qubit. We can take a look at the simulation I made previously, and we can see from the LOM that the frequency of our qubit is around 5 gigahertz, and from the paper it's quite similar. There is minor difference. The coherence time um, is also very similar. Mm, there is also frequency of resonator, and that's all we basically care about. Now let's take a look at the softwares we will use. We will need AVR, which you can have free trial. We will use this for lumped elements. Then we move to Jupyter Notebook. Its environment for Qiskit metal. Then we will need some FEM simulator. You can also have free trial or student license. Uh, then we will need FreeCAD to export 3D files, and we will need Blender for visualization. Let's do lump simulation. For this we will use AVR. We need to create new schematic. Once we have this done, we need to take a look at the paper to know how to actually create lumped elements schematic. It's from the paper called Circuit Quantum Electrodynamics. We can scroll down to see. This is a representation for resonator. Here we can see a representation for transmon qubit. It uses Josephson junction and shunt capacitor. Here is our connection of transmon with resonator. You can see that the blue one is resonator and the green one is transmon. And we will need this one to replicate, or alternatively the picture above. Here. So for this we will first need to calculate resonant frequencies of a transmon and coupling bus or resonator. We will use online calculator for this. We need to pass capacitance, which is about usually 50 femtofarads. Then we need to pass inductance. You can see that resonant frequency for our qubit should be about 5 gigahertz. So we can add these values to AVR. For resonators, we typically have inductance of 15 nanohenry. So our schematic should look like this. We need to pick resonator. and we also need to pick capacitor. We need to change values, so we will do project options, global units, edit units. We'll choose femtofarads, nanohenries, and gigahertz. For this, we will have 50 we will say 45 femtofarads and 15 nanohenry, and this is a small capacitor, and we will choose a value of 5 femtofarads. You also need to add ground. This is our um, for qubit, we should use Josephson junction, but since we only need S parameters and impedance profile, we can also use just inductor, because FEM simulator uses also just large inductor instead of Josephson junction to compute electric fields and EPR. So for this, we can use just inductor. If we need more advanced simulation, such as simulating currents and other parameters, we should use Microwave Studio with built-in Josephson junction model. You need to change this to 20 nanohenries. Now we need to add what's called graphs, new graph, rectangular, uh, measurement, dB, all sources as parameters, and we also need to add measurement for port 2, which is our qubit. We will also want a graph for impedance profile, so we can scroll down and select Z. We will have impedance profile only for resonator. Now we need to change project options, frequencies. We will start at frequency of 1 GHz and stop at a frequency of 10 GHz, and we will have step of 0.001. Now we have our graph of impedance profile, then we have our graph of S parameters. Here is S parameter for qubit, and here is S parameter for resonator. We can change labels by changing this value. This is a resonator, this is qubit. We can now close this and move to the layout. For this, we will need to use Qiskit metal. So we jump to the Python, and here you can see our file. We start with importing important libraries. Here is our pill library for image import. Here is our Qiskit metal definition, and here is our PyAPR. So we run this command. Now we define our design here. Um, Here we start our GUI, and there is a definition of chip plane of itself. This is the ground plane of a chip. There is a size of a chip, and there is offset from center. We usually define this in the last step where we know how big our design is depending on our components. Now, before we start designing, we will need to add our transmon. For this, we will use transmon pocket 6. So we will go into the libraries, qubits, and transmon pocket 6. We create one, and now we need to modify it. To do this, we can modify this in a Python script because we need to add our pins. You can see there is no connection paths available. There is just connection path A. We need connection path B as well. We save our design, we click save, and we save it. Now we have our Python script saved. We can open it using Notepad, and all we need to do is copy this command with import of transmon pocket 6 and paste it into our Python script. I've already have this transmon here. All we need to do is copy this A pin parameters and options, paste it and rename it to B and change some parameters. So we run this step to see this. Now we have our transmons defined. Let's take a look at our first transmon. You can see that, well, now we have our connection paths A and B. In order to change a position of our pins, we need to adjust these two values. You can see a location width and a location height. We can do this by changing this to either +1 or -1 or 0. We can see -1 is down here, +1 is up there, 0 is at the center, and we can do the same thing with the other option. So this is on the other side. This is on our correct side. We can also change pad width and pad height. So let's change this value to see. You can see the pad is now bigger. We don't need to adjust any other values, so we can all leave it as it is. For the central flux tunable transmon, all we need to do is to choose transmon pocket with charge line and do the same thing with our pin definition. We need to add another pin B in a script. So let's take a look for other components we have there. The other component is called line T, which is very simple. All we need to define here is orientation, position, X, which is horizontal position, and position Y, which is vertical position. Mm, You can see our line T here. Mm, So there is not a lot to define here. We can move to another component which is called launchpad wire bond. There is also very little to define. There is only orientation, position X and position Y. So we execute this step. We can see our launch pads are here. We have 7 launch pads. We need to delete this transmon, which was just for example. We have 7 launch pads. We can take a look. The upper ones are at the position of 4,000 micrometers, and the lower ones are at minus 2,000 micrometers, and with orientation 90 degrees. We can jump to other step, which is route mixed. In this step, we need to define a few things. I'll execute this step and show you a split screen so you can see it properly. We have our route mixed number 1 here. We need to define few things, which is start pin. In our case, it is LT1. So we click at LT1 and see for this pin we will use second end. So we need to write down here second end. And for end pin, we will use component LT4, which is this one. And we will use second end as well. So we will write down second end here as well. The other parameter we have here is lead, which basically tells us the start straight of meander from the beginning. So in our case, it's 200 micrometers from the beginning, so it forces the meander to be straight to this place. Next parameter is anchors. For this, we defined the points which forces are route mixed to route are meander. In this case, it's the first point is 0.5 and 0, which is here. The other point is 1.83 and 0, which is this one, and the last one is 1.83 and 1, which is this one. So we have 3 points, and now we need to define a style of our road. So we can see from the point 0 to our first point, so it's from the beginning to the first point. We force it to be S, which is straight, so the meander is straight. Then from the first point to the second point, which is here, we force it to be M, which is a meander, so we can see it's meandered here. And from the second point to third point, we force it to be straight as well, and then from this point to the end, we force it to be straight as well. So that's for the anchors. Now for the fillet, I can actually show it to you more visually. Fillet does basically how the software should round the edges of the meander. So if we change the value to 150, you can see the edges are not rounded anymore. If we do 120, maybe 100, or maybe 70, you can see the edges are a little bit more round. If we say we want 90, the edges are nicely rounded. Then the other value is total length, which tells us the length of the meander or the whole road. We can force it to be 14, so you can see the meander is very big. Next, there is meander options, which basically tells us how the meander should behave. There is spacing values, which tells us the spacing of the meander. If we change this value and lower this to, let's say, 140, you can see the meander is more dense, but it also affects the fillet value. So if we say we want 220, the meander is quite big. It's not that dense, so you can see um, there is also another value which is called asymmetry, which shifts our meander to the one side or the other if we add minus sign. And this is all we care about in meanders. For the other meanders, the process is quite similar. All we need to do is set up pins, anchors, total length, meander, spacing, and asymmetry, and we should be fine. So we can execute this command, and we have other meanders. Next step, we need to route this line T with our qubit. For this, we will use route straight. We have two parameters, which is start pin and end pin. For start pin, it is our component LT1, which is this one, and we have our you can see we have our prime start, and we can connect it with qubit on. We can connect it with qubit 4 and pin A. This is basically it. It's very simple for route straight. So we can execute this command. Now we can add our logo, we need to choose correct naming for our logo. We need to have it in our repo here next to the our Python file. We need to copy name and paste it here. We can set location by adjusting offset value, and we can adjust scale. Here we can draw each rectangle, so it's not just a metal layer, but also nice edged frame. The same is for our icon. We can have our logo and icon as well. So we can execute this and wait a few moments. Now we have our logo and icon rendered. We can move to Time Simulator. We can open a new project. Um, new project, new HFSS file, um, and we will render HFSS simulation. You can see it is rendering. We need to wait a little while. Now we will simulate our resonator. We need to assign ports. So we do this by assigning citation port, lump port, add integration line, new line, and we need to do the same thing on the other end. let me oh, I just open this one, add setup, add frequency sweep. We will need frequency from 1 gigahertz to 10 gigahertz, and we will have 4000 points. We need to add results, create a rectangular plot, S11 parameters, dB, and sweep. We need to do the same thing for impedance profile. Now we click Analyze All. Let's see, there are some messages. Non-manifold vertices. So all we need to do is to delete this one and run Analyze All again. We can clear messages. Once we have our simulation done, we can take a look at our plots. It looks quite okay. And we can do simulation of capacitances. We will need to export this project into Q3D. Now we'll click assign boundary rate in conductor, perfect electric conductor, about 200 nanometers. Now we define our nets. Now we click analysis, add solution setup. DC and AC, we will unselect this. We only need capacitance. We will click OK. We will click on results. Create matrix lab report, rectangular plot. Now we choose adaptive bias, C matrix, absolute, and we choose pad gate, gate ground, pad 1 ground, pad 1, pad 2, and that is all we need. Now we click simulate, analyze all. Once our simulation simulation is done. We can take a look. And now we can see capacitance from pad 1 to ground around 50 femtofarads, which is our capacitance we simulated in lumped element simulation stage in microwave office. We have other plots, which is pad to pad, which is around 30 femtofarads, and the other ones are below 10 femtofarads. Now we will move to simulation of only 1 qubit for EPR and electric field simulation, because simulation of the whole system would be very computationally heavy, so we will simulate only 1 qubit. So let's get started. To execute first few commands, here's our definition of EPR. Here we start HFSS. Here we activate design. Here we render our design. Here we choose properties for our qubit. And we click analyze. It will take a while. Now we will need to plot our fields. In this step, you can see plot of our fields. Here's mode number 1. Here's our Josephson junction. We'll clear fields and set mode 2. Here's mode 2. Now we will run EPR. We'll set up. Here we choose our name of Josephson junction, rectangle and line. We can find the name here in Fem Simulator. And we will click run EPR. You can see some values from EPR. We care about this value, which is EPR of substrate. And you can see there are two modes. Mode number 0, which is at around 6 gigahertz, and mode 1, which is cavity mode, which is 48 gigahertz. Now we will jump into LOM analysis. Here we render our qubit into Q3D. We need to specify a name for qubit, which is Q4 in our case, and we need to select pins properly, which is A, B, and charge line in our case. We set up our sim. We run our transport pocket. We need to choose correct name for this, which we can see in our in our code here. Here, transport pocket. So this is our name. We can take a look at the outputs from the LOM simulation. You can see there is our frequency of qubit, energy of capacitor, and energy of junction. Inductance of our qubit, and the coherence time. um, you can see there are values for capacitance from Q3D simulator, which we simulated manually. Now you can see some values here. Mm, um, Now we have values we care about. And we can pass them into SC qubits. All we need to do is copy these parameters and paste them here. Just be careful, this is in megahertz, so it's like this. Here's our wave function of transmon. We can take a look at energy spectrum, and we can also take a look at the coherence time, which is here. We can select effective T2 and scan over EJ, so we can see our decoherence plot here. Once we have this done, we can generate GDS files. We will generate GDS files from this layout. We'll select location. We'll call it my design. We select fabricate true, and that's it, and we can click export. We can view our GDS files in ABR. We just need to open this, and here's our GDS files for fabrication. Now we will export our quantum chip into Blender and create preview. So we will click modeler, export as a step file, and we will call it chip. We will save it. And now we can open our quantum chip using FreeCAD step file and export it into Blender format. Now we will select all the shells and click export as object file. We will call it chip as well. We can close this. We can open Blender. I already have Blender tutorial pre-made example. This is our scene. It uses plane, light, and camera, and this is our quantum chip, which it's already done, but I'll show you how to do it from scratch. So we will delete all the shells. We will import, or we can just drag and drop it. Here's our quantum chip. We will move it horizontally, scale it down a bit, rotate using R. By clicking X, we can rotate it. We will click 90 degrees, minus 90 degrees. We will move it upwards by clicking G and Z, and we will move it closer to the camera using G and X and Y. Now we have our quantum chip. All we need to do is to select our plane, click Shift D, G, and Z. Now we will click tab. We will select all the edges. We will click Shift D to duplicate, G and Z to move it. We'll move it by 5. We will click wireframe, delete all the geometry here. Now we will delete. Now we will click let me is there any here's our geometry. We'll select it and delete it, all the vertices. We'll need to go to wireframe, delete all the vertices. Let's do it again just to be sure. Now we will select our frame, click F, and now we will drag it down by clicking G, Z, and -5. We'll scale it down a bit. We'll click 7 to see. Now we will scale it. Extrude it by clicking E. We will extrude it by 0.07 in that direction. We will go upwards with our second plane and we will extrude it as well. and we will assign materials. For this, I already pre-made some materials. To see materials, we need to go to the materials tab here. We can click material 001, and for this we will choose color 1, and here's our quantum chip. We will go to camera, render image, and here's our quantum chip. So that's all for quantum chip design, and hopefully you enjoyed this tutorial.